In this lecture, we will talk about linear projections. Imagine that we have the wine sales up until yesterday, and we put that into a vector x, and we want to predict how much wine will be sold tomorrow, and we have that in the vector y. So we want to describe how much do we know about y, given that what we have observed. So given that we have seen the wine sales all the way up until to yesterday, how much can we predict of y? Obviously, I mean, we can use, there's a lot of information in it, so we should be able to predict quite a lot. But how do we do that? And the answer is that we want to use a conditional expectation. And what we do is that we take the vector y and we project it, use a linear projection, that is a conditional expectation. A linear projection for a Gaussian is the same thing as expressing the vector that you can form by taking the previous measurements, scaling them, and adding an offset. So that is a projection. So I have the range space of x, that is the same thing as all the points that I can reach by taking the vector x and scaling it by a complex number. So any point that I can reach is in the range space of x. So what I do is I take the future vector, the y, and I project it onto the range space of x. Then what I get is I get this p point. That is the conditional expectation of y given x. What is the value I expect y to take given that I have observed x? That is exactly our prediction. Here, the point to notice also is that even though that it is obvious that but the vector p here lies in the range space of x, it does not have any component that is outside of the range space of x. Obviously, I cannot describe my estimate other than using the data that I have seen, so I cannot observe things that are in the future. The future, that is what is not in the range space of x. So here you can observe that the vector orthogonal to the range space, that's the error, that's the difference between the actual future and my prediction of the future given what I have observed, that's the vector e, that is going to be orthogonal to the prediction. And that's exactly how we want it. We want to be able to extract all the information that we can from the observations we've had, use that to make the prediction as good as possible. And if we do that, if we can make it as good as it possibly can get, that means that the error that we are making is going to be orthogonal to the observation. There is no further information in the observations that we have that we can use to improve our prediction. Then that is going to be the optimal one. This is called the principle of orthogonality. And it's a quite important principle. And this is what we will use when we design predictors in the future in a part of the course. But basically what we're trying to do is that we try to minimize the error, making it orthogonal to the data so that we get exactly this fact that the prediction onto the range space and that is the future, then and the part that is the future, that's the error, that part we cannot describe, those two are orthogonal to each other. No further structure can be given. And as you see, just by geometry, the covariance between the error and the data is zero. We will also look at cases when we split the data. We want to do recursions later on. We will observe the data up until now, and then we'll say, what if I get one more sample? How can I make a recursive update so that I don't have to recompute everything all the time? So to be able to do that, we concatenate the data. We say, this is the y here, that's my measurement all the way up to the time before yesterday. And this is yesterday. So what I'm trying to get now is what is the best thing I can do in a recursive manner using the previous estimate and then just the additional point that I got yesterday. And what means that if I concatenate this into matrix Z, I will have a concatenated covariance matrix, which has the autocovariance matrix of X, autocovariance matrix of Y, and then I will have the cross covariance matrices here. And the linear projection will then be possible to express like this. So this is going to be the future. I mean, this is, if you ever wondered what the future will bring, well, this is the answer. It's the linear projection of the future onto the range space of X. And that will be the mean vector as well as the scaling given the covariance matrices like this of the offsets. So this will be the optimal linear projection. You cannot make a better projection if you require that it's to be linear. That means that there will be no other projection that will have smaller error. I can also express the variance like this, and as you see, it will only depend on the covariance matrices here. So if I do know the covariance matrix, I am able to express exactly what the error I'm making when I'm trying to predict the future. Obviously, I will never know those, but I can estimate these covariance matrices, and of course, then I can make an estimate of how well do I trust my prediction. An important point to note is that if x and y are normal distributed, then the error and the data as an observation are going to be independent of each other, which is of course a very strong statement. But even if they're not normal distributed, these two will be uncorrelated, which is of course quite helpful.